Hi, I'm Tommy Thompson and welcome to AI 101, the series that explores the tools and techniques used in video game development. The opening episodes of this series have taken a look at some of the long-established AI methodologies used in video games, with navigation meshes and finite state machines being two of the earliest techniques to become commonplace. In the second episode, I looked at behaviour trees, a technique popularised by the Halo franchise in the mid-2000s that has since arguably become the most commonly used method for controlling non-player characters in the AAA games industry. In this episode, we take a look at the other technique that achieved popularity at the same time, and in keeping with the channel recently reaching 100,000 subscribers, thank you all so much by the way, you're friggin' awesome, what better time to return to the technology and the game where AI in games began. Let's take a look at goal-oriented action planning and the game that popularised it, First Encounter Assault Recon. To understand goal-oriented action planning, and in turn how it's used in FEAR and many other games, we need to take a look at the theory from which it derives from, an existing AI technology known as automated planning. Automated planning, or AI planning, is a process whereby a system attempts to figure out a sequence of actions that will achieve a distant goal set upon it by a designer. This set of actions is then called a plan. To do this, we model the problem in some sort of language or encoding that tells us all the information that can be true about the world at any given time. These are known as facts or predicates, where a simple fact tells us something we might need to know at a later point in time. We store all of the predicates we have about how the world looks like at any point in time within what's known as a state. For example, here's a door. We'll call it Door 1, because it's important to give the door a name, and this door is closed. But I might want a non-player character to open Door 1 at some point in the future. So I need to know in a predicate whether it's open or closed, because opening a door that's already open is kinda stupid. So the current state of our world is one closed door. Now, given I have this information, I can build an action that allows me to open it. Each planning action is usually broken up into three parts: the items that are involved in the action, in this case a door because we want to open it, the action's preconditions, meaning what facts of the world must be true before I can apply the action, and the effects, which represent how the world changes as a result of completing the action. The effects of an action adds new information to the world state, as well as possibly deleting existing facts that are no longer true. So say I want my non-player character to open Door 1, some valid preconditions for an open door action would be that the door is closed and that the non-player character is standing in the same room as the door. Once the action is completed, the effect would be that the door is now open. Now say we wanted to walk our character from room A to room B, but the door between them is closed. We would need to make sure in our planning model that we explain that Door 1 connects room A to room B, and that you cannot walk between rooms if there is a closed door. At which point, the system will create a plan, which is to open the door, and then walk from room A to B, changing the state of the world to where the NPC is now in room B. In a nutshell, this is what planning is all about: figuring out what to do and in what order to do it. This process of encoding problems and allowing for planning systems to solve them is why it has been an active and developing research field for decades. While FEAR helped bring planning to games in 2005, planning has previously been used in a variety of real-world logistics problems as far back as the 1970s. This includes problems such as robotics, ranging from smaller home-based devices to the likes of the Lunar and Mars rovers, control of large-scale mechanical systems such as wind turbines, power stations and manufacturing, and in complex spatial problems such as search and rescue operations, military planning and disaster relief. But my explanation hides some of the nastier details underneath. These planning encodings rely on humans being able to abstract the problem we're solving into something simple for a planner to solve. Returning to that door opening problem, I said that the NPC needs to be in room A and that Door 1 connects the two rooms. This works fine in a planning model, but there's a bunch of discrepancies between the model and how that would work in real life or even in a video game. For example, where in room A is the door to room B? What direction does the NPC need to move towards the door? In fact, in the planning model, the NPC can open the door if they're in a room that the door connects to, meaning this wee fella is now apparently telekinetic and can open doors with their mind from very far away? This is in contrast to a more realistic interpretation, which is that not only does the NPC need to be in room A, but it also needs to be standing right next to Door 1 in order to open it. Hence, while planning is great for solving the larger problem of what to do in a given situation, executing the plan of action in the world, be it in the real world or in a video game, is a lot harder. So now that we know what planning is and how it works, let's take a look at goal-oriented action planning and how it brings AI planning to video games. Goal-oriented action planning, or GOAP for short, adapts what is known as STRIPS planning, the Stanford Research Institute problem solver, a planning system from 1971 for use in video games. Leading development on this project was Dr. Jeff Orkin, the AI lead for Monolith Productions on both 2002's No One Lives Forever 2 and 2005's FEAR, where GOAP was first implemented. As detailed in Orkin's 2006 publication at the Game Developers Conference while studying his PhD at the MIT Media Lab, the GOAP system is driven by a finite state machine. As detailed back in episode 3 of AI 101, a finite state machine is a system whereby an AI exists within one state of behaviour and then based on an event occurring will transition into another one. As we explored how FSMs are adopted in Half-Life, we found that there was over 80 unique states that existed in the game's codebase. Although whether that state was available was determined by the type of character that the state machine was controlling. However, here in GOAP, the finite state machine has only 3 states: moving into a position in the world, playing an animation, or interacting with what is known as a smart object, an item in the world that AI characters can communicate with. Now, you might be a little confused how this works, but it's all based on a really clever observation of how non-player character AI works. If you consider an AI in a game, be it the headcrabs in Half-Life, the elites in Halo, or even the xenomorph in Alien Isolation, all they do is play animations in very specific circumstances. It's when that animation is played in the right place at the right time, it appears clever, and when several clever animations are played in a sequence, it appears intelligent. Hence, each of these 3 states within the GOAP FSM is ultimately playing an animation. Go-To is playing a movement animation, be it walking, running, jumping, diving, or climbing, but it's also heading to a specific location. Animate is simply playing an animation. This could be acknowledging the player's presence to shooting their weapon, or any simple idle animation which would give this NPC a bit more character. And lastly, use Smart Object, which is a situation such as having an NPC hit a switch, open a door, sit in a chair, or knock a table over. In each case, the animation is tied directly to the object, and quite often in games, such as that found in my episode on the AI of Bioshock Infinite, the object will tell the character's animation system what it needs to do. So, instead of a more grounded state machine where each possible behaviour is enumerated as a separate state, the whole thing is executed in a much smaller and highly data-driven implementation. It will execute specific movement actions and animations that are passed into the system, and if several movement, animation, and smart object states are executed in the correct sequence, we'll get some smart-looking behaviour. But how does it know what states to be in what order should it go through them, and what information is to be passed into each state? Well, that's where the planning part of GOAP kicks in. Using a planning encoding like we talked about before, the system creates plans that solve specific problems in the planning encoding and uses A* search to find the best actions to take in solving the problem. The actions within the resulting plan are then translated into specific FSM states, with data being passed, such as locations to move towards, animations to play, and smart objects to interact with. To better understand how this works in practice, let's crack open the hood of FEAR and explore how GOAP is adopted within the game. So let's take a deeper look at how GOAP is applied in FEAR. Portions of the game's C++ codebase have been publicly available for some years now, first with the original FEAR SDK being released by Monolith, followed by the FEAR public tools as modders have continued support for it. And with very little effort, you can crack it open in Visual Studio and read through the AI source code. So let's walk through how GOAP is applied within the codebase, and for those wanting to try their hand themselves, I've left links in the description for you to check out. Each AI character in FEAR that has any sort of AI needs to have goals assigned to it. These goals are ones that the planner will run a search through the action space in order to find a plan of action for that character to execute. This applies to all active non-player characters in the game, from the soldiers and assassins to the nightmare spectres at the end of the game, and even the rats that are running around on the ground, which is a super important point I'll come back to in a minute. This means that the other characters, such as Jin Sung Kwan and Jankowski, and even Alma herself, are all scripted by designers. Without a goal, the AI characters will do literally nothing. They need to be given goals to accomplish, which the planning system will aim to resolve. There are just shy of 70 goals encoded within the game's files. In each case, these goals can be initialized, updated, and terminated, and more critically, have functions that allow for them to calculate their overall priority at that point of time in the game. So, for example, if a soldier has been assigned the patrol and kill enemy goals, but it has no knowledge of the player being nearby, then kill enemy will have a priority of 0, while patrol has a much higher priority given there is a patrol node that's been assigned to that character. However, in the event that it has knowledge of the player being nearby, the patrol goal will have a much lower priority, given it recognises that the player is now a threat to it. Now, in order for the planner to solve that goal, the character will have a collection of actions available to it that it can search through. There are 120 actions in the game, ranging from simple animations to different attack variants, moving to locations, using smart object nodes, reloading weapons, or just standing idle, all of which have their own corresponding C++ classes. The actions are set up in code, but not all NPCs have access to all actions. The game's designers use a separate database editor to assign specific actions to each enemy type, allowing them to customize just how versatile that character will be in solving their goals. With a goal assigned to a given character, it will await a chance to access the planner and find a solution to its current situation. This is where the larger issues I hinted at earlier in the video come to light. The system needs to find actions that this particular character can execute, search through the possible actions within the state space, find a plan that reaches the goal, but all of this needs to be revalidated against the game during execution. This is because something can happen either during planning time or when executing the plan that can break it. Returning to my door example from earlier, if you're generating a plan to open the door and move between rooms, but during the planning process or as you're executing it, the door is opened by someone or something else, it will then invalidate that plan. This is an issue that the vast majority of planning systems face, in that they're rather existential in nature, and assume that only the planner can change the world, so it can't accommodate for other characters doing stuff in the world as part of the plan. In fact, as mentioned in the original FEAR video, none of the enemy AI in FEAR know that each other exists, and cooperative behaviours are simply two AI characters being given goals that line up nicely to create what looks like coordinated behaviours when executed. Not only are they unable to walk towards navigation points in the world where other characters are standing, but have zero knowledge of that character's existence. Hence, if another character does something that would break the proposed plan, then each character needs to be able to recognise that, so it stops what it's doing and it asks for another plan, or even change the goal if necessary. This is handled in 3 different ways. Firstly, once a plan is devised, the system will then run a quick validation check. It takes a copy of the current game state, executes the plan on that copy, and ensures it will satisfy the goals as intended, with each action's preconditions and effects working as hoped. Secondly, each goal can override the replan required function, which continually checks whether the current plan should be abandoned and a replacement one be retrieved from the planner. A good example of this is when an enemy character is shot while executing a plan to satisfy the kill enemy goal. However, this is only allowed in the event the character is not executing an animation that cannot be interrupted. Lastly, each action in the plan needs to be validated again during execution, with preconditions and effects being checked. In the event they are not satisfied as intended, the system will bail out the plan and force a replan to occur. However, if that action is going to work as intended, the action is activated in the codebase. When that happens, it tells the finite state machine which of the 3 states to transition into, and passes over all of the data it needs to complete the finite state machine's execution. So, say for example, a soldier needs to reload their weapon, then it transitions into the animate state and passes in the specific animation parameters that are needed so that the character will reload their gun. Once an AI character completes their devised plan successfully, it will then be assigned a new goal and can plan again. By managing both when plans succeed as well as when they fail, this helps maintain the pace of the game, ensuring the AI always knows what to do and don't stand around idle waiting to be slow-mo shot in the face. In truth, the length of plans in FEAR are often rather short, typically 1 to 2 actions long, with only a handful ever reaching 3 or 4 actions in length. This largely makes sense given the overall pacing of the game. That said, this goal management and planning process does create a problem, one that even the developers at Monolith didn't know about for many years. As detailed in a 2014 research paper by Professor Jacopin, in which he analyses the performance of the GOAP planner in FEAR, It's discovered that this process of continually replanning creates a small performance overhead in some levels of the game, thanks to the rats. The rats in F.E.A.R. are, as I mentioned, using the same system as the soldiers and other combat AI. Typically their plans are really simple. Move to another location in the world and preferably away from the player if they're nearby. The need for the rats to replan doesn't take into consideration whether the player is nearby. Hence, you can meet a couple of rats in the opening seconds of the level, and they'll still be running around planning for new actions 20 minutes later while you're on the other side of the map. This is far from an exhaustive overview of the codebase, and I do encourage anyone who can work their way around C++ to have a read through the code. It's really insightful and rewarding for game developers to get their hands on. F.E.A.R.'s use of goal-oriented action planning is still held to this day as some of the most exciting and fun enemy opponents to come across in modern video games. And while it's now been almost 15 years since the game's release, GOAP has continued to have a lasting impact within the video games industry. While far from an exhaustive list, there are many highly popular games and even cult classics that have adopted the methodology or something similar to it. This includes the likes of Condemned Criminal Origins, Stalker Shadow of Chernobyl, Just Cause 2, Deus Ex Human Revolution, the 2013 reboot of Tomb Raider, and more recent titles by Monolith such as Middle-earth Shadow of Mordor and Shadow of War. There are other episodes of AI in games that have explored its applications, such as Transformers War for Cybertron in episode 14, as well as a heavily modified hybrid approach in Empire and Napoleon Total War back in episode 22. Planning is still a popular technique in video games, though arguably not as common as, say, behaviour trees. But over time, GOAP and its strip-style approach is now being adopted less frequently, with more contemporary titles adopting another planning technology known as Hierarchical Task Network or HTN planning. HTN planning has been used in titles such as Killzone 2, Max Payne 3 and Dying Light. I'll be dedicating a future episode of AI 101 to this topic, but I've already covered the implementation of this planning method in detail for Transformers Fall of Cybertron, also in episode 14, and Horizon Zero Dawn, over in episode 37. But for now, I hope this helps everyone better understand not only why people continue to laud the AI of F.E.A.R, but also the underlying technology being adopted. I've listed some other useful resources on goal-oriented action planning in the video description for you to check out. Thanks for watching this episode of AI 101, and a special thank you to each and every one of you who has subscribed to and supported the channel. Breaking 100,000 subscribers is still relatively small by YouTube standards, but still much larger than I ever envisaged for AI in games. AI 101, alongside all my other series here on the channel, is crowdfunded over on Patreon. If you'd want to join our community and have a say in future episodes on the show, join the AI in Games Patreon using the links on screen and in the description. Stay safe, have fun, and I'll be back.